of ASGSR and until Saturday that I'm president. And it's a great pleasure to welcome you here and to the Science and Technology session, where we worked to bring in the NASA chief scientist and chief technologist to talk about what's ahead of us. And so we have Dr. Jim Green, chief scientist, and then standing in for Dr. Douglas Terrier, who Sunday night had to cancel out, is Dr. Tara Rutley, and associate chief scientist for exploration and applied research. And Jim asked me to be brief, give most of the time for he and Tara. So welcome, Jim Green.
Thank you very much, Stephen. So what I'd like to do today, indeed, is talk about forward to the moon and then on to Mars. It doesn't mean we're leaving the moon, of course. It means that we're going to also continue research at the moon. Now, what I thought I'd do is provide a little backdrop of what we believe has been the evolution of the Earth and the moon from a planetary perspective, and why we think the permanently shadowed regions are really rich in volatiles. Here, of course, is our first human exploration at the moon, starting with Apollo 11, 12, 14, 15, 16, and 17. These were all on the near side of the moon. I watched them. I was in high school. It was just an exciting time, grainy TV, etc. But we're really in for an exciting next era with high definition TV. Also, the shadowing will be very eerie. It'll look much different than the Apollos, I can guarantee you. And it'll be very engaging worldwide. Now, what did we learn from the Apollo program was an enormous amount of things. For instance, we brought about 850 pounds of lunar material. These included regolith, cores, also a variety of samples from each of these areas. And from that, we began in our laboratory equipment really teasing apart the fantastic information that's available. Now, what comes from that has been a series of models, theories rather, that proposed the origin of the moon, which is intimately tied to the Earth. And the theory that has really gotten the most attention is called the giant impact hypothesis. This is where the early part of the solar system, as the proto-Earth was accreting and materials coming together. An accretion is a violent process for which two things collide or more things collide, and then the gravity brings them back, creating a larger object. Well, the giant impact hypothesis has two major objects collide. One, a Mars-sized object that planetary scientists commonly call Theia, and then the proto-Earth. And this is early on in the final stages of putting the Earth together. In the first few million years after the sun started hitting the main sequence and began the process of clearing out the nebula and creating the solar, much more like the solar system that we see today. Now, a Mars-sized object hitting the proto-Earth produces an enormous rearrangement of those objects. And in fact, Theia is literally destroyed, pieces of it everywhere. And we know from planetary observations, even of Saturn, that there's an area just outside the planet for which that material cannot accrete, but will fall into the planet, creating a larger body. And that's called the Roche limit. Outside the Roche limit, you're far enough away from the main body that you then can accumulate more material and create another body. And of course, we believe that body then was the moon. Now that means the moon actually is just outside the Roche limit 4.5 billion years ago, all right? And in fact, one day on the Earth was probably on the order of 5 hours. if you were on the Earth at the time, and I wouldn't recommend it because it was very hot, still cooling off, and looking up, the moon would dominate the sky, 16 times larger than what we see it today. Just at that distance of about 4.5 or so Earth radii away from the Earth. But over time, due to tidal forces and tidal dissipation, the moon moves away from the Earth. And then, of course, that gradually slows down the Earth, creating one day being 24 hours, tidally locking the moon, and then we end up in the time period today where the moon is about 60 Earth radii away. So this is a really important theory that allows us to understand then some of the observations from the Apollo. As Clive mentioned, we have retroreflectors. We hit those retroreflectors every year, all the time, since they were on the moon, 50 years or more. And what we find is the moon is moving away from the Earth about 1.5 inches a year, okay? And that process is going to continue. Now, in this early period, of course, we're also being bombarded by asteroids. These objects are carrying water. We know that. We see asteroids out in the asteroid belt, many of them a significant amount of water, and a lot of volatiles. They're now impacting both the Earth and the moon, and then hopefully bringing material to the Earth that perhaps is that next start after the Earth cools down, where the volatiles come back through these bombardments of comets and asteroids and provide an environment such as bringing amino acids to the Earth that then perhaps have started life. There was another really important epoch that happened not too long after the moon and the Earth were formed, and Barbara mentioned this. This is a period of time called the Late Heavy Bombardment. And this was about 500 million years after the Earth and moon were formed, and the moon is moving away from the Earth continually, as I mentioned, and by this time it's probably on the order of 15 Earth radii away, all right? And this bombardment was enormous. What we look at the moon, we see the mare. The mare, of course, are large impact regions for which most of the crust is blown away, and the lower crust or even upper mantle of molten rock is pouring into these large cratered regions we call basins because they're big, and filling that up with lava and basaltic material from the interior. Current research seems to indicate during this time period that the moon therefore must be outgassing. And calculations seem to indicate that this bombardment was so extensive that perhaps the moon developed an atmosphere on the order of 10 millibar. Well, Mars is about 6 or 7 millibar. And so this actually is a very significant lunar atmosphere. Now that's recent results. It needs to be proven out. We can do that by bringing back the right samples and really trying to tease out that understanding. As Barbara mentioned, there are some conflicting data on exactly when the late heavy bombardment happened and over what time period. But new research is indicating that from the samples we brought back, that the moon had a magnetic field. It generated a magnetic field. In particular, during this time, it was probably one of the intense time periods of the magnetic field generation by the moon. Therefore, the moon had a magnetosphere. And this magnetic field also provides an opportunity to protect the atmosphere of the moon and let it hang on to it for tens of millions of years. Now, within 100 million years, the moon's magnetic field wanes. And as it does so, then the solar wind is going to be really stripping the rest of the atmosphere away as it dwindles over time. But indeed, once you have an atmosphere, then the volatiles are going to migrate to the cold traps. They're going to go to the north and south poles. And so in addition to the bombardment by asteroids and comets carrying volatiles hitting the moon, and that material migrating also to the cold traps, therefore the polar areas, you have potentially an early lunar atmosphere. Not only that, with the magnetic field that the moon has generated, we know the magnetosphere of the Earth, we believe, has also been quite steady from early on when it went through the proto-Earth Theia impact and came out on the other side of that, generated its magnetic field. The two magnetic fields can intertwine, allowing Earth atmosphere, actually, early Earth atmosphere, to move then to the polar caps of the moon. So now you have even potentially more volatiles that are there. All right, so what Tony has been talking about, and Clive and Barbara, of course, is these wonderful areas that we have found in the last decade or so, and more research has been uncovered, that these permanently shadowed areas that are old areas on the moon, and some even the younger ones, then have been accumulating these volatiles. And they're cold, some of the coldest places in the solar system. And this means that indeed, what we may find in these cold traps is quite an array of volatiles. One would expect that as we dig down, perhaps we can find the volatiles from the early comet and asteroid bombardments, perhaps lunar atmosphere, water, carbon monoxide, carbon dioxide, sulfur, many other volatiles, Earth potential atmosphere, both nitrogen and oxygen. And then we know also what's currently happening today. There is a small water cycle on the moon. The mission Laddie, as it flew in the 2012 time period and orbited the moon, saw clouds of water bursting all over the moon. And what we find out by analyzing that data and comparing it with meteor showers is that they are coincident. So what we're finding is during meteor showers, these micrometeors that are bombarding the moon is also liberating water, which then has an opportunity to migrate, in addition to being ionized and lost by the solar wind, but to migrate to the polar caps. Now, this would be great if we could get a stratigraphy that shows this, but we're not, all right? It won't be as clean. We know the moon is constantly bombarded with micrometeors, so these layers will be mixed up, we anticipate. But we don't really understand or know in a significant way, because we haven't measured it, we have modeled it, how much of the micrometeors are really hitting the polar caps and producing the gardening that would mix these layers up. So indeed, this is a tremendously important time to be able to start studying these. Now, as mentioned, permanently shadowed regions are great accumulators of this material over time. The current estimate is there's probably several 100 million tons of water trapped in these areas. But if you're going and extracting that for resources, such as oxygen, there might be a significant amount of oxygen in carbon dioxide or carbon monoxide or other oxidized material that comes from the early lunar atmosphere. Now, of course, observations have indicated that in blue, these are the areas that we see from a couple instruments, one in particular on the Lunar Reconnaissance Orbiter, indications from their gamma ray neutron experiment. Cosmic rays come in, interact below the surface, neutrons come out, but that's inhibited by water, and therefore by looking at that neutron gamma ray flux, we see these regions which have very low fluxes, indicating regions of water. So this is really tremendously exciting from that aspect. Now, as we also talked, how are we going? Well, we're going there with partners. We have a slew of commercial partners that we're working with. These are groups that are under contract, and as we then have calls for opportunities for instruments, we also then put out the right call to this group, who then proposes that they will take experiments that NASA will be building to the moon and be able to start executing them. Now, of course, none of them have landed on the moon yet, okay? So we're in that heady early days of exploring, and as you probably know from the history, I was there when it was going on. I was alive and interested in what's happening. NASA launched a whole slew of lunar missions, and the first 4 or 5 didn't make it. We either missed the moon when we wanted to crash into it, or we couldn't get into orbit, or just a whole variety of problems. So hopefully we're in an era where we now have the capability, particularly from our aerospace industry, to make huge strides and be successful on even their first attempts. Now, as Barbara mentioned, the CLPS vendors are providing rides, not only in the southern hemisphere, but many other regions of the moon. These other regions of the moon are extremely important, as I mentioned earlier, because we have a lot more to learn from looking at the samples to determine if some of the models and our understanding of that evolution of the moon, late heavy bombardment and lunar atmosphere, interaction with the magnetic fields of the Earth and the moon is true or not. So we have a lot of work to do in that particular area, and many of these missions will start attacking some of those questions that we'd like to have answered. And in fact, of course, the first few missions that will be landing will begin in 2022. So this next year will be an exciting opportunity for us. And then we're planning to have 2 a year from there on. Now, also, there are orbital opportunities. And as you can see, and as Barbara mentioned, we have the Artemis mission dropping off CubeSats, but we also have opportunities for lunar missions, lunar CubeSats, other things that are coming up, particularly with international partners too, wanting to be involved. And so I anticipate this next decade to be an enormous number of lunar missions. Now, what you probably don't remember, I do, before we landed on the moon, we had more than 25 missions that NASA did to examine and understand the region before humans went to the moon. So indeed, planetary science was that group, that initial set of explorers that went to the moon, landed, understood the basic environment, looked at the sun, flew through the Van Allen radiation belts, understood the radiation environment, at least at some elementary level, such that that gain of knowledge enabled us to be confident about going to the moon and really exploring it. So in a similar way, we're now putting the icing on the cake by using the knowledge we've gained from that era to really tease out what's happening in the evolution of the Earth-Moon story. And then, of course, it provides us a fabulous opportunity to do a variety of research in this area. So, indeed, as Barbara mentioned, the Artemis program has a whole suite of missions going. The first 3 Artemis missions, the first uncrewed, then a crewed capsule, doing a figure 8 around the moon, and then finally Artemis 3 having the opportunity to be able to land on the surface of the moon with humans, and that will be a wonderful time, and I know it'll be riveting for all of us to be seeing what's happening. Another aspect of that is, of course, the Gateway. The Gateway will be built soon after the Artemis missions begin, and the Gateway will have an ever-increasing capability. The Gateway, of course, is in a highly elliptical orbit over the South Pole that enables then rapid communication with surface assets and even assets on the far side of the moon, which we have not really explored other than remote sensing from our orbiters. This is a fabulous opportunity. The concept of having the Gateway where high bandwidth data can come back to the Earth. High bandwidth being not only data, but video, high resolution, high definition TV aspects, in addition to audio. Those all have to be supported to be able to help support humans on the surface, but it will enable in major ways a lot of the science that we want to do. The Gateway, as I mentioned, right now is being thought about as having several international components. European Space Agency and JAXA, Japanese Space Agency, will participate. Current payloads are indeed in the area of space weather devices and other types of radiation detectors. But that discussion is just beginning, and there is perhaps other opportunities that may come up. Now, where we're going to land on the surface of the moon is several areas are being considered, hasn't been determined yet, all right? So conceptually, we want to be able to do a lot of the kind of analysis that Tony showed, where we are landed in a nice, safe level. You know, this whole area is really quite a rolling area, plains and heights and etc., which causes areas of degrees of shadows, as really shown earlier. And so we have to really play that off to come up with the right place. The kind of things that we're seeing, of course, on the moon as resources is hydrogen, oxygen, nitrogen, carbon, fluorine, sulfur. And then, of course, there's the elusive helium-3. You know, is that a potential source for energy or not? Of course, the things that we want to be able to do is study as best we can here on Earth, but take opportunities as we can to be able to have plant production on the moon, and how we do that, and what resources are available for us to do that. And so many of the technologies that are being developed are in support of these activities. So you have large amounts of space power. Currently, we're working with the Department of Energy for 10 kilowatt systems that should provide power. That'll be also probably connected with alternate forms such as solar arrays that then also provide supplementary a set of power. We're doing a lot in the area of in situ resource utilization, you know, being able to know what's there, therefore be able to tease out what those resources are and then understand how we would use them. We also are thinking of, in major ways, 3D printing, the ability to take the resources, regolith is a perfect example, and be able to create structures or habitats that would enable and protect us indeed from the harsh environment of the solar wind. And then, of course, there's ion engines, or what we also call solar electric propulsion, the ability to have a gas, ionize it, and then with an electric field, shoot it out the back of the spacecraft, and then that momentum allows us to be pushed forward. So what is the future of the moon? Well, we want to continue that science, and we want to continue exploration. We want to figure out and learn how to live off the land. You know, this is our first opportunity, as Clive mentioned, to create a really sustainable program. And to me, that means a long-term presence on the moon, leveraging and using resources as much as possible, whereas what we take, there's little or no waste, and we continue to recycle it, and there's many different ways that we ought to be able to implement and do that. Learning to live and work on a planetary surface starts with the moon. What we learn from that we'll then take to Mars. And then, of course, there's many other things that are possible, perhaps a fuel depot, mining, manufacturing, etc. Now, the elements then that we're developing, as we talked about, learning to live and work on a planetary surface, we also want to feed forward to our Mars program. So that means, you know, the moon is performing that analog to us for Mars. What we learn, we want to be able to apply. Now that means vehicles. That also means the ability to learn how to manage in a lunar dust environment the similarities with a Mars dust environment. And then, of course, be able to get resources, in particular water, etc. Now, Mars provides its own challenges. You know, as we know, it has a very thin atmosphere, and that thin atmosphere really is a problem for landing anything. And we think our first foray into landing and working on the moon from a human exploration perspective is that we need about 40 tons worth of material on the moon to then assemble before humans get there. And I'll remind everyone, we've only been able to do 1 ton, and that's Curiosity and Perseverance. So the moon, though, or sorry, Mars, though, has a whole series of missions that are up and running now. Not only from the orbiters that do the relay, but we have a lot of unlanded assets. We have InSight that's looking and measuring how active the moon is, Mars is, and it's measured about 600 or 700 Mars events or quakes. And of course, we have Perseverance and Curiosity, with the next big steps going to be indeed sample return. Curiosity made a huge step when it landed in Gale Crater in an area that we now understand had a significant amount of water. It drilled below the surface. This is the first 2 drill holes. They're about the size of a dime, and the deeper one is about 1 inch or so deep, and it was very surprising. Below that red patina we see as the surface of Mars, that oxidized surface, there's gray Mars. And then when we looked at that, we found that the mineralogy was really very exciting because it has all the key elements that we'd like to see: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The soils had nitrates in them, and they were also moist. The next big rover, of course, is there on the surface. It's Perseverance, and Perseverance is designed to core rock, creating a core about the size of a piece of chalkboard chalk. And for those students in the audience that never used a blackboard, it's about the size of a Crayola crayon, the large kind. And we've sleeved that. We're going to lay these on the surface, and then that allows for pickup and then return. We have about 43 sample tubes, and that's the material we'll bring back. And the area we're going to is Jezero Crater, and it's this upper part. The upper left of this image shows the delta, where a river that inflowed, dropping sediment as the crater filled up. The outflow is where we finally broke over the crater wall with the water and flowed into the ancient ocean. All right? So 4 billion years ago, Mars was a blue planet with a significant amount of water and had rivers and deltas that flowed. And this is actually the right region to be able to go and really tease out and create the samples necessary that we will bring back. And of course, how we'll do that is after we lay them on the surface, our next mission, perhaps as early as 2026, we'll go and create, with another rover, creating the opportunity to grab up the samples, bring them back to a Mars ascent vehicle, which we will load, erect, launch. Samples then will be orbiting. We'll get into orbit, pick them up, and then return them to Earth. Now, we're also going to do in situ resource utilization. This includes really with these samples, understanding the toxicity of the soils, okay? Understanding their pH, understanding, could Mark Watney grow potatoes or not? Or is it more, instead of acidic soils, more alkaline soils that we see with Curiosity, and therefore it would be more asparagus and beans? Who knows? We have a lot of work to do in that area. And then finally, the area on Mars that we will see is this exploration zone. That's the plan. For many decades, the plan is to go to an area and consistently, unlike the Martian, which went to different areas, we're going to go to one area, one exploration zone. In that zone, we're going to land in an area, live in an area, and do ISRU, but also be able to do a variety of really tremendous and exciting science before then we return. Finally, yes, Tara's back. Let me all right. Let me introduce her. Next, let me tell you that there's a lot of synergy in our biological aspects. in terms of what space biology, planetary protection, and astrobiology is cross-cutting. Not so much planetary protection on the moon, but Mars will have to worry about looking for life. Our big effort in astrobiology, in developing technologies that will do that, that include unknown life. But of course, what we want to do here is use technologies to monitor the health and function of life, human life. All right, so with that, let me introduce to the podium Tara Rutley, our Associate Chief Scientist, to talk more about our next big steps.
And I will interrupt. Thank you, Jim.
You're very welcome.
I will interrupt and point out that there will be a question time after Dr. Rutley with the usual 855 number. Thank you. Go ahead.
Yeah, thanks, Stephen. Okay, I am not Douglas Terrier. Most of you probably recognize that. I'm Tara Rutley, Associate Chief Scientist for Microgravity Research and Human Exploration, working with Jim Green. Doug couldn't make it today, so they asked me to share the stage. Jim asked me to share the stage with him, which was actually a great honor because I've been working with Jim Green for the last 3 years, where I came up to headquarters to work with him from the Johnson Space Center, where I worked in the Space Station Science Office for about 10 years. So to share the stage with Jim is really, really cool because it kind of reflects what he and I had been working on, whether you know it or not, up in the Chief Scientist's office. It's also very cool because Jim is retiring in January, and I have not shared the stage. So this is a great time to share the stage with Jim. And I would say also, when question time comes, get him while you can. Ask the questions that you want to know of Jim Green today. And also, he's not really leaving. He's going to stick around and be an emeritus. So we're thankful for that. So when I was asked to come and fill in last minute, I said, yeah, well, this is a great community. I grew up with you all, whether you knew it or not. I've been following you since I was like in high school, college, when you were ASGSB biology, and I was a biology student. So I thought, boy, I grew up. I get to be on stage finally. So what would I say to this community? How do I use my time best? And that is to say thank you. First of all, for sticking around. This community, you have a heart and a work ethic that goes back decades. You have the experience and the expertise, unlike anywhere around the world, that you are space scientists and do important work. You all are the ones who motivated me to want to join the space program in the first place. And kept my interest going. I was a graduate student and undergraduate student here at ASGSB. I was doing the posters. I won an award. I wanted to be like you. So it's great to now be among you and to see all the young faces out there as well. So welcome to the community now that we are ASGSR and that we're combined physical and biological sciences, which is a strong show of good faith and good experience going forward into what we're headed towards, which you heard a lot from Jim. Now, so today I figured the cool thing to do would be to kind of wax poetic about my career and my experience with you all in this industry, knowing that we have had the last 20 years of people living on the International Space Station doing the important work through times of the last 20 years that haven't always been so easy for you. But you managed to your heart's in it, and you've stuck around and want to share some of the fantastic work that you've been doing on station. But not only that, but now we're at the point of a decadal survey, right? So we are at this inflection point of looking back at the last 20 years and looking ahead at the next 10 years. And you all, I know, have submitted white papers to the decadal and have these images and these dreams and these ideas of where this community needs to go. If you were around, you heard from Thomas this morning about his ideas. And it's been fascinating to see you all adapt to the new plans we have in the next 10 years. And we're talking Moon and Mars. So I'm going to talk a little bit about both and from my perspective. And, you know, I might just ask for some interaction from some of you introverts too, as we move along. But I wonder if you raise your hand if you recognize what this image is. 1, 2, come on, more of you know what this is a picture of. Yeah, thank you. Participate, you introverts. I know you can do this. That's Space Lab, right? That is what I grew up with. I grew up with watching these astronauts do experiments in spinning chairs and do experiments with bubbles of water and fire and different types of tiny creatures. And that is what I loved. That is why I wanted to join NASA. It wasn't the rockets, it wasn't the vehicles, it wasn't the cool astronauts, you know, in their suits. It was the science. I was a science nerd. And so that is the path that I decided to go down. I decided to go down the biology path. I ended up in the Space Station Science Office at Johnson for the last 10 years, like I said. And I started in 2001. So when I came to work at NASA, we had just sent people to the International Space Station, Expedition 1. We've been since, as you know, last year we celebrated 20 years of our time in space. And I want to first put a thank you and a shout out to the Research Integration Office down at JSC, because these are there. They made these awesome charts. The science communication team made these charts and they let me use them for today. So kudos and thank you to them. So even back then, back in 2000, Expedition 1 started, they did over 50 different investigations back then. And we weren't even talking about the science. We were talking about building the thing. But they did Earth observation, they did plasma crystals. Most of you are familiar with plasma crystals in this room, I think, and you're also probably familiar with viral shedding. So some of the basics that they started with have evolved over the last 20 years. Look at where we are now. We are now this majorly capable laboratory. We survived budget cuts. We survived reconfigurations, not full space station that we'd expected as a scientific community. The promises that were made early on. Look how far we've come. All of you in here have had a hand in that, and it's everywhere from microgravity to astrophysics to observing the Earth, right? These are all part of what this vehicle designed to do science in space has provided us over the last two decades. And we've grown. And what I did was, I went back and I went through all my old presentations, like from when I first started at the Space Station Science Office, so starting in 2009 and 10, when we were trying to start developing messages around the cool science that was being done on station. And literally, I just took this out of an old presentation and plopped it in. Does anybody know what this is an image of? I mean, it says so on the bottom of the screen. Yeah, I see in a hand. Oh, I see you back there, Liz. This is Mark Weislogel's experiment. If anyone in here is associated with Mark Weislogel's lab, I know you're a bunch of introverts, but can you stand up? Anybody here from Weislogel's? There we go. Oh, yeah. Hey, Ben Cat. Good to see you. Yeah. Right. So to me, I went way, way back. And Mark Weislogel's work was so simple. Capillary action, just studying fluid behaviors in space in different geometries of different containers, creating models that did not otherwise exist in the previous decades that we've already been flying in space. And now if you know how the fluid behaves and you can model it, you can create better propellant tanks and water tanks and things like that. So this is how we started, very, very basic. Another very basic, stand up if you're associated with this one. This one's a big one. Anybody in here associated with the Flex 2 experiment? Or are you just going to be an introvert and keep sitting down and try to get under my radar? Okay, fine. So if none of you are in here, you probably have heard about it. This was a big buzz when back in like 2012 when we first went from assembly complete to utilization, and this happened. This happened was a lighting up a liquid fuel, right? Heptane, I think it was, in the combustion rack on station. Fine, we thought we studied the flame, we thought it went out, and then we got the secondary flame here called a cool flame, right? That blew people's minds, you may remember. And now, even as of this summer, we've started studying, what are these cool flames? Well, it's a flame that's emitting, it's reigniting based on just the chemicals that are left over in the environment. It has nothing to do with us lighting it. It's when you thought the flame went out, but guess what? It didn't. It's kind of like a reignition of a fire. Well, that's important because cool flames can help us learn how to, improve our combustion engines on Earth and burn cleaner fuels and things like this, and also understand how to suppress fires in space. Okay, who's tried protein crystal growth in space before? I know y'all are out here. There's a hand there. Anybody? Raise your hand. Okay, yeah, you guys in the front. I know you have. Anybody else? Raise your hand. Look around you, everybody. So protein crystal growth goes way, way back. And it's sometimes it works and sometimes it doesn't. And it's the lack of convection and sedimentation and buoyancy that are driving some of the harder to grow crystals on Earth, or we're using them to try to grow in space. And we've had some successes. This is an old slide, again, old. I say old, 2010. I guess it is old, it's 11 years, where our Japanese colleagues sent up a crystal conglomerate of a protein that's involved in Duchenne muscular dystrophy. You've probably heard this story. This was a big one. They grew up this crystal and better understood the structure of the inhibitor, the medicine, the treatment with the crystal of the bad protein for Duchenne, grew it up and found a new hidden water molecule there in blue. And that was all they needed to let them then go back to the labs and create improvements on their treatment of Duchenne. And so we're improving the quality of life, and this was a big one. And so protein crystal doesn't always work out that well, and we've tried since then. We've sent up lots of experiments, especially through the national lab, and some have been a better success than others, but you guys aren't giving up, and you're keeping on and you're keeping moving, and we need that, especially where we're thinking about going in the future. Another thing, hey, when I was a kid, astronauts were losing bone and muscle, and we knew it. Since our time on station, we've gotten really good at understanding what's going on there, and we have found that if you do your increased resistive exercise, you eat all your calories, you take all your vitamin D, your big doses of vitamin D, we've managed to solve that. We've managed to mitigate bone and muscle loss. There's still some question about the structure of the bone. Those are details, but it's a fascinating thing. I mean, we have done on the International Space Station to enable exploration. That's what we want to do. That's what we are trying to do. So congratulations to the community for that. Now, again, we have had over 180 research tools and facilities. We've done over 3,000 experiments, and we have represented over 4,000 scientists from over 100 countries. You are truly global. You have done things, and we have done things like grown heart cells, got them to beat in microgravity, blown Kate's mind with that kind of research on orbit. And we are now working on tissue chips. These are the future. These are the national lab. These are the space biology things that are growing from the tiny little start points that I share with you to something now big that the community is recognizing we might have a future in, not just for exploration, but for development of low Earth orbit economy. Colloidal behaviors, I know some of you are out there. This is cool. This is a video from station talking about smart fluids, how you can manipulate colloids and the particles within them because you don't have sedimentation on orbit. You can look at that, the nature of dark matter. You all have heard about benefits to humanity, the robotic surgeries that have come from the Canadian arm, for example, the makers of the Canadian arm, and cleaner combustion. That image, right, that video of that flame, that is part 2 of the earlier flame that I showed you. We had follow-on experiments now, purposefully driven experiments on cool flames and combustion. And now we've got these beautiful new lines of research we had never expected to get before. Cool flames are hard to develop on Earth. 1 minute. Yeah, satellite deployments. Now we're going on to commercial industry, manufacturing fiber optics. Some of you are in here. We're evolving. We're enabling exploration. We're talking about ECLIS, surviving the human beings. I have to mention technology because Douglas isn't here, and this is supposed to be a technology part. But free flyers, technology for resurfacing satellites and going to the moon and ultimately Mars. We're using station for all of these things. Got to do a shout out to Joya and the progress that we have made in growing our crops. You guys, we were killing plants in the beginning. We're growing chilies now, and they're making headlines. And they're eating. The astronauts are eating right. Thank you. The astronauts are eating what they are growing. That is the point. And now you all and me, we're all facing a new commercial low Earth orbit development. Well, we're given a brand new challenge, just like we were 20 years ago and 10 years. Here we go again. You all have a role. You're the experts in creating a low Earth orbit economy. We want having folks out in space. We want more access. But not only that, you're going to also be busy on the moon. You are already in conversations and in workshops and making your way through the Science Mission Directorate to get your biological and physical payloads on the moon. But what's missing from here? I see a habitat. This is a conceptual design of Artemis Base Camp. I see a habitat. I do not see a lab. I don't see a lab, and there should be a lab. There's real estate for a lab that's dedicated to your work. And so I hope that you recognize that and you push for that and do not take anything less than that. It is your opportunity now. You as scientists in the scientific community, I mean, more than ever, what a time to be a scientist right now in the space environment. Remember, I'm out of time, but your work is essential for all of our agencies' major goals. Low Earth orbit economy. You're going to talk to commercial providers while you're here. Find out how you fit in. You fit in. Your work is essential for Artemis, going back to the moon. Have those conversations. Go to those workshops. Dream big. Apply and talk to people. This is not just talk, right? This is real. We need you. You're our experts. And your work is ultimately then essential for Mars. And you heard Jim talk about what we need to go to Mars. That may seem way far off, but the work you're doing now for low Earth orbit and the moon is going to be leveraged for Mars. So you are important for all of our agencies' goals. And I went way over time, and it's time for questions. So
thank you, Tara.
That's it for me.
The text number for questions is still 855-855-1413. I've got a couple here. In the theme of science and technology, these lunar missions and Mars certainly involve long-duration cryogenic propellant storage and usage, and cryogenic refueling in some proposals. That's kind of a mix of the science between the fluid physics and the technology of making it happen. Are there joint SMD, STMD programs aimed at really getting this historic first of cryogenic refueling and weightlessness up and running?
Yes, there's a lot of discussion right now in STMD about that particular area. How that is connected to SMD is probably not as strong as I see it as it could be, but the discussion is just now beginning. As Tara mentioned, technologies are incredibly important because they enable the science that we want to do. And so, once again, providing input into the decadal is critical to be able to delineate the technologies that are needed to support the community into the future.
Yeah, and the cryogenic storage was one of the first success stories that I know BPS was so proud of, having done something on orbit as an experiment and really making the connection with STMD, and now going to be taking it through likely to the moon and applying it. I mean, we've done a lot of things, and sometimes they don't make it all the way to applications as right away as this one has. But this one is a good example of the working relationship between the two, and BPS getting out in front and sharing what you've done fundamentally that can be applied.
Okay, and shifting gears and combining a couple of questions here, going back to the topic of water on the moon, ice on the moon. Is there expectation of microbial or other life frozen in there, and how would we detect it, and how would those detectors be proven out before the mission?
That's a great question, because indeed many communities are interested in looking at that, not only from the astrobiology community, but also in the area of planetary protection. Because planetary protection has international guidelines in terms of forward contamination. We want to be able to not contaminate an area that may harbor life, and backward contamination about bringing material back that could affect life on Earth. So currently, the moon is in a very low category in planetary protection. So we believe that indeed there's no way life could be supported on the surface. The fact that the volatiles that are there are early volatiles from comets. There may be amino acids, but we don't anticipate life. And that would be true not only from other volatiles that are there that could be part of the lunar atmosphere, et cetera. So what we want to do when we go into the permanently shadow areas is indeed understand what other missions may have contributed volatiles, even propellants. And so going in certain regions at high latitudes in both the northern and southern hemisphere, one has to report the amount of volatiles that would be laid on the surface that may indeed migrate into the permanently shadowed area. Once we require that, that will be posted on the COSPAR website for everyone to use and be able to understand and interpret their data. And as Barbara mentioned, once you know what's there, you can identify those signals as, okay, we brought that, but here's the really important things that we want to look at. So it's not a problem. But it is a concern, and there's ways to address it.
And then for the audience, we have run a little bit long, and we'll wrap up with another question here is, given, obviously, like everything we do, there's limited resources and limited money. What would your vision of a version 1.0 lab on the lunar surface look like, and what instruments and science would be in it?
Yeah, well, we just submitted a white paper to the Decadal about this. So what would the lab look like? Well, it's up to the scientific community to tell us what it should look like, but it would be thinking about a combination of whether, is this lab going to be actually part of the habitat? Is it going to be a separate standalone? And if it's a separate standalone, will it be pressurized, or will it be kind of an afterthought place where astronauts might put automated instruments in, like a garage, and maybe attend to them when they go in and out of EVA, right? So you can do crew tended, you can do crew untended, to support all the biological, the physical sciences, the fundamental experiments that you would require. And these discussions will actually be happening within NASA over the next year. We have ways to start talking about this. Now, NASA's already talked with the BPS community about possible case uses and what those facilities might look like to support the types of science, but the range is wide. I mean, how do we want to prioritize? How do you want to prioritize the type of work, biological and physical sciences work, to be done on the lunar surface? Is it enough to have crew untended and automatic payloads that are off to the side and unpressurized, or do you want a full-size lab that can support sample processing end to end? Or do you want to return your samples home? But so complexity of the investigations is up to you to communicate that, right? Especially at a time during the decadal study. And a lot of what we go forward with next, of course, will be a result of the decadal study. But crew tended, untended, pressurized, unpressurized, is a part of the HAB? Is it a secondary thought, not part of the HAB? These are all things that we will be talking about in the next year or two.
I might mention, if I may, I was head of planetary science from 2006 to 2018, and the planetary decadal that I received was really quite aggressive. It had many more things in it than I could possibly execute, certainly with the NASA budget. But that decadal also enabled me not only to build a better budget through the right arguments over time. So when I started in planetary, the budget was $1.1 billion, and when I left, it was twice that, at $2.2 billion over that 12-year period. Enables you to do that, to build that program. In addition to that, we could execute a number of the things that were in the decadal through partnerships. It enabled me then to approach ESA about sharing resources, being part of a mission concept that they wanted to do, that then we could put the right instruments on their mission that would enable us to indeed make progress in our decadal. So an aggressive decadal that you can't execute, in my opinion, is good, not bad. It allows us to really begin thinking about the right investments and opens opportunities for the international partners. The Artemis Accords, which are NASA's first international agreement to work together, has 12 or 13 signatories on it at the moment. And I believe once humans begin that process of going to the moon on a more regular basis and landing, that will radically increase. And many of those countries are first time in the space program and want to be part of the space program, want to have an opportunity to build an aspect of a laboratory that may be sitting on the moon, and then engage their scientific community. So the richness of the decadal is so important, it really opens up new vistas that you then can move into.
Okay, before we wrap up, I want to mention a few short things. 2 o'clock is the policy panel session. Before that, if you're interested, at 12:30, there's membership committee meeting and journal committee meeting. Those committees are made up of ASGSR members like all of you. You can attend. And also on my app, at least, I got a nice message that the app is going to provide me, whoever gets it, with information on local lunch options. And so that can be a good resource at this time because there's a lot of us, and clearly pandemic has affected in-house restaurant here. So thank you very much, Jim and Tara. I appreciate it a lot, and thank you everybody for your questions and your attention.
Thank you very much. Thank you very much.